Hey everyone! Today I'm going to revolutionize how you think about drone batteries. By the end of this video, you'll know how to use nanotechnology to achieve lighter, more efficient and longer-lasting batteries for your drones. First things first, let's talk about the materials you're going to need. You'll need nanoparticles like carbon nanotubes, CNTs, graphene oxide and silicon nanoparticles. For the battery materials, you'll require lithium, cobalt oxide, graphite, and electrolytes such as LiPF6. Don't forget your solvents, acetone, ethanol, and water. Conductive additives like carbon black and conductive polymers are also essential. Finally, you'll need synthesis equipment such as a homogenizer and a furnace, along with battery assembly tools like a coating machine, pressing tools, and a coin cell assembly kit. All right, let's dive into the protocol. Step 1. Nanoparticle synthesis and characterization. For carbon nanotubes, you have two options. Synthesize them through chemical vapor deposition or purchase high-quality CNTs. Ensure the proper morphology and structure using SEM and TEM. For graphene and graphene oxide, use the Hummers method to synthesize graphene oxide from graphite. Reduce it chemically or thermally to form reduced graphene oxide and validate the quality with Raman spectroscopy. Silicon nanoparticles can be synthesized using the Sol-Gel method or bought pre-synthesized. Characterize them using SEM or dynamic light scattering. Step 2. Synthesis of nanocomposite materials for anode and cathode. Mix CNTs or RGO with graphite to create a composite material for the anode. Add silicon nanoparticles to enhance the specific capacity and mix with a binder like PVDF and a conductive agent like carbon black. Coat the electrode with a doctor blade technique and dry it at 60 degrees Celsius for 12 hours. For the cathode, use traditional materials like lithium cobalt oxide or nickel manganese cobalt. Improve performance with nano coatings such as TiO2 or Co304. Fabricate the cathode using a similar process to the anode. Step 3. Electrolyte preparation. Prepare an electrolyte using a lithium-based salt like LiPF6 in a solvent mixture of ethylene carbonate and dimethyl carbonate. Enhance stability with ionic liquid-based additives, especially for high-capacity anode materials like silicon. Step 4. Assembly of the battery. Construct a coin cell battery using the fabricated anode and cathode. Add the prepared electrolyte and assemble the coin cell using a crimping tool. Now onto cycling and testing. Perform initial cycling using a galvanostatic charge-discharge test to evaluate performance and specific capacity. Conduct cyclic voltammetry and electrochemical impedance spectroscopy to assess the electrochemical behavior and stability. Step 5. Performance evaluation. Calculate the energy density using the formula energy density equal sign voltage V x capacity R mass kg. Test the battery at different current rates to evaluate high rate capability and cycle it over 500 cycles to monitor capacity retention and voltage stability. Use a thermal chamber to test performance at varying temperatures from -20 degrees Celsius to 60 degrees Celsius. Step 6. Analysis and optimization. Analyze the specific energy and specific power to ensure the nanoparticle-enhanced battery outperforms conventional ones. Use SEM to check for structural degradation or nanoparticle dispersion issues during cycling. To wrap up, leveraging nanotechnology can significantly boost drone battery performance, making them more lightweight and long-lasting. Dive into these recent research citations for deeper insights. Huang et al., 2023. Chen et al., 2021. Liu et al., 2020, and Zhou et al., 2019. Stay tuned for more cutting-edge research tips and tricks. Thanks for watching, and don't forget to like and subscribe.